On my roll number is 34. Today I am here to present the SS PPT presentation. My topic is analogy between vectors and signals. This presentation includes into the correlation between vectors and signals and highlighting the idea of the orthogonal signal space and complex orthogonal system. This concept plays a crucial role in the various domains such as communication, control systems, and signal processing, in illustrating the significance in the efficiency managing and interpreting data. This slide is about my data. Understanding signals and vector spaces. Signals are functioning that convey information and play a crucial role into the terminal telecommunication. Vector spaces in the mathematics offers a framework and multiple understanding multi-dimensional phenomena that can be applied to signals. This analogy is essential for improving understanding the fields of communication, communicating, control, and the signal processing systems. First one, importance of signals. Signals convey critical information across various applications. Second one, role of vector spaces. Vector spaces helps analyze multi-dimensional phenomena related to signals. Applications in technology. Understanding these concepts enhances the systems in communication and processing. Vector space fundamentals. First one, definition of vectors. A vector is an entity that has both magnitude and direction. Second one, vector space properties. Vector space allows for scaling and adding of vectors with the specific properties in operation. Third one, geometric visualization. Vector can be visualized in two or three dimensional spaces respecting physical quantities. Signal representation as vectors. Mapping, first one, mapping signals. Signals can be represented as vectors by mapping them to points in the higher dimensional space. Discrete signal view. Discrete signals can be viewed as sequences of vector components in a finite dimensional space. Engineering applications. Vector representation helps in processing signals effectively in engineering applications. Inner product for signals. Mathematical basis. The inner product measures similarity and projection in the signal spaces. Second one, continuous versus discrete signals. Continuous signals use an integral. Discrete signals summation like dot products. Quantity relationship. It essential for various signal processing tasks. Orthogonality in vectors. First one, definition of orthogonality. Second one, importance of orthogonality. Third one, application of mathematics and physics. Definition of orthogonality. Two vectors are orthogonal if their inner product equals 0, meaning they are perpendicular. Second, importance of orthogonality. Orthogonal vectors minimize interference in the various applications representing distinct directions. Application in mathematics and physics. Understanding orthogonality offers fundamental instinct into the mathematical and physical applications. Orthogonality in signals. First one, definition of orthogonal signal. Orthogonal signals have a zero inner product, allowing independent manipulation. Second one, classical example of orthogonality. Sine and cosine signals of different frequency are orthogonal used for decomparison. Third one, importance of signal processing, critical for developing methods to distributing overlapping signals. This is the diagram for orthogonality signals. Orthogonal signal spaces. First one definition, second one expression, third one examples. A orthogonal signal space compresses signals that can be used as basic foundations for representation similar to vector space. Expression and signal can be expressed as a linear combination of these orthogonal basis functions providing various analytic advantages. Examples such as Fourier series. This concept showcase how signals can be decomposed into their frequency concepts. Energy and norm of a signals. Definition of energy. The energy of a signal is defined as the square of norm connecting it with vector length in terms of signal power. Understanding signal properties. This relationship lays the groundwork for understanding signal behaviors and properties, adding in the analysis and designing. Parseval's theorem. Parseval's theorem further enhances this connection, how energy in the time domain relates to the energy in the frequency domain. Understanding complex signals. First one, complex valued signals incorporates imaginary components for comprehensive representation. Second one, Irul's formula converts complex exponentials to sinusoidal signals. Analyzes technique simplifies analysis and enhances understanding of signal characteristics. Complex orthogonal systems. First one, complex orthogonality. Orthogonality applies in the complex domain with the high high maintained inner product. Second one, significance in exponential signals. Distinct frequency maintain independence in the representing these signals. Third one, applications in communications. Maintaining distinct signal paths is crucial for effective communication. Applications in communication and control systems. First one, communication techniques. Second one, signal optimization. Third one, control system design, modulation and orthogonal frequency division, multiplexing are vit- vital for data transformation. Signal optimization, signal compression and noise reduction enhances integrity and optimize storage. Third one, control system design, understanding signal spaces, IDs in the designing effective feedback. Virtual interpretation. First one, diagrams and connections. Second one, geographical representation. Third one, complex signal visualization. First one, diagrams and connections. Diagrams effectively infiltrate the connections between vector space and signal space, aiding in visual understanding of concept. Second one, graphical representation. Graphical representation of orthogonal signal can enhance comprehension of their unique properties and functions. Third one, complex signal visualization. Visualizing complex signal is a complex plane aids aids in the grasping their behavior and application. Analogy of vector spaces and signal spaces. First one, vector spaces and signal spaces. Second one, orthogonal basic functions. Third one, complex orthogonal systems. Vector spaces and signal spaces. The analogy between these spaces highlights the significant similarities. Orthogonal basic function, recognizing their important facilities, advancements in the communication. Third one, complex orthogonal systems. These systems enrich our understanding for various engineering applications. References and questions. Relevant sources include relevant books, articles, or lecturer notes that were utilized in developing this presentation. Questions invite questions and discuss to clarify concepts and further deeper understanding among participants.